So today we're going to talk about have a brief overview of the alternatives for Psibase consensus and the properties that they have, and then we'll get to a demo using this to set up an actual network. So in the network, you have a couple kinds of nodes. You have the block producers that are the nodes that actually accept transactions and produce new blocks. You also have a number of non-voting nodes that can serve various roles. They can act as relays, or they can serve content to humans, or to act as API endpoints for other programs. For the rest of this talk, I'm going to pretend that those non-voting nodes don't exist. They don't participate in consensus. All they do is follow the consensus established by the block producers. So also out of scope for today is how the block producers are actually chosen. We're just going to treat it as some set of block producers is chosen in some arbitrary manner. We don't care about that for the consensus algorithm. They are set programmatically on chain. Any service that has sufficient permissions can just write to a magic database record to tell the nodes what those block producers are. So any consensus algorithm has two key properties that we want to guarantee. The first is safety. The second is liveness. So in the context of a blockchain, safety means that different nodes won't end up following different forks. They will eventually converge to the same chain. You can create as many forks as you want, and they can be as long as they want. But when we decide that one fork is irreversible, that's it. Only one of those will ever become irreversible. Liveness means that the network continues to produce and commit new blocks. Just producing blocks without committing them is not really liveness, since you actually have to commit them before anything external to the chain considers that to be real. So what I've described here is a fairly weak liveness guarantee. In a real chain, eventually we probably want to have a guarantee that covers transactions submitted to the chain as well, and you expect them to either succeed or to fail. That hasn't currently been implemented, and I haven't really figured out a good way to formalize such guarantees. So at the moment, liveness just means the network produces and commits new blocks. So the first alternative consensus algorithm is based on RAFT. The properties that it has are that if a node fails, we expect it just to halt. That is, it can stop responding, but if it ever produces incorrect results or just lies, then all bets are off. So this isn't really useful for an adversarial environment unless there's some kind of out-of-band enforcement. It's mostly useful for trusted producers or to have failover in a single producer network. The advantages of RAFT are that it's relatively simple and therefore less likely to have bugs, and it also allows more nodes to fail before the whole network grinds to a halt, and it has lower latency because of it has fewer things to deal with. So for RAFT, you only need a simple majority of the nodes. So 51% live and you're good. The stronger form of consensus is a Byzantine fault tolerance. For BFT, there are no restrictions on how nodes can fail. They're allowed, if a node fails, it can produce invalid messages. It can send different contradictory messages to different peers. And safety and liveness are guaranteed as long as the number of nodes that fail is bounded. So you need more than 2/3 of the total block producers to be operating correctly in order for the network to function. This is the theoretical minimum that is possible. It's not possible. There's no way to do better than the 2/3 majority. All right, so here we have a quick comparison of the algorithms. So for BFT, you have a higher threshold of nodes that you need to be live, 67% versus 51%. You also have a 50% greater delay before blocks become irreversible. And the protocol is also quite a bit noisier. Note that messages per block is the total messages across the whole network. Each node is only going to see some subset of those. So, demo time. First of all, I'm going to launch 3 nodes here. So I'm running all of these nodes on localhost. For a real network, you'd probably want to run them on different machines, but I'm just going to run them on different ports here. So this is the first node running on port 8080. Now I can start a second node on port 8081. And I can start node C. Let's start that on port 8082. All right, now let's configure those nodes. Okay, so we want the nodes to accept PDP connections. We should give it a name so it can produce blocks, and we want it to have the WASM HTTP API enabled, which is accessed through this URL. Okay. So we'll then do that for the other 2 nodes as well. Okay, so now we have 3 totally independent nodes running. We want to link them together, so we can do that through the Pures page. And that's 2 connections. And then the last one. There we go. Okay, so now we have all 3 nodes fully connected. Next thing we need to do is to boot the chain. So right now there is no blockchain. We need to create a new chain that's run through the Psibase boot command. So we're going to say that block producer A is going to produce blocks to start with. We will change that later. Let's see if this works. All right, so you can see this node is producing blocks. The other 2 nodes are receiving the produced blocks. So this here is A. All right, so the next thing we're going to do is we want to switch the network to use RAFT with all 3 of these nodes. So before we do that, we need to generate keys for each of the 3 nodes, which is kind of a pain right now because there isn't the proper interface for it. So this API endpoint will generate a new key for the server, assuming I got the syntax right. Let's see. Yeah, there we go. So that is a new public key for node A. Let's save that for the moment. So this is A's key. Now we'll generate a key for B as well and save it. And the same thing for C. Okay, now in order to set the consensus algorithm, we'll want to go to there we go. So this is the interface page for the producer's contract, which allows setting the consensus algorithm and the set of producers. Currently, it's very minimal and requires entering the transaction in JSON. So it's already set to CFT, which is RAFT. or crash fault tolerant. Let's build that. So in this, we want to list all three producers. And now we're going to copy in the public keys that we got here. Let's see if that works. And it looks like it worked correctly. So we see in the log the transaction succeeded. Now this node is producing blocks. Let's kill it. And this node just took over. So now I can start up this node again. And it should catch up again. There, we're caught up. And I can similarly kill that node. And now node A is building. As we can just randomly kill and restart nodes, and it'll just keep chugging away whenever two of them are active. Similarly, if we want to use BFT, we just go into this, and instead of and replace it like that. For BFT, you would need at least 4 nodes instead of 3. I'm not going to do that here because it'll look almost identical. I guess that's it for the demo for today. Any questions?
Thanks, Stephen. I probably have a couple questions, and just wanted to clarify too that, so what those interfaces that you all just saw Stephen using, those are part of the chain, right? So if you run Synode, you have those configuration interfaces in that web interface that you can access to configure the node, which is a really cool user experience. And the producer sys service, that area where you saw Stephen entering the JSON and it looked like a very early stage interface, those interfaces ought to be and will be improved over time to become more clear and less like you're just entering raw JSON. But yeah, I hope that it's exciting for you, if you're watching this, to see that those interfaces are served from the chain, and so you can see directionally the end goal here is to have really clean ways for people to configure their nodes, even for something as esoteric as defining what consensus mechanism you want between your nodes in a multi-node deployment.